Good day, guys. So today in this session we'll basically go through the water treatment stages again, but the difference now is going to be will involve some calculations that are involved, as well as going into depth in terms of explaining each of these water treatment stages, because there is vast information that we still need to go through in order to understand each and every one of them. So the first one, basically under preliminary treatment, as we had said the previous time, we'll have our screenings. After our screenings, we'll then have our pre-chlorination. Basically, we had said under our screenings, we will be removing solid particles, larger solid particles such as bigger rocks, cloth, plastics, and so forth. Okay. After then we'll have our pre-chlorination. Basically, our pre-chlorination is a stage whereby we'll be removing, we'll try and control algae so that it doesn't go further whilst it's going through other treatment stages in terms of the flow of the water. And then lastly, under preliminary treatment, we'll have our grit channels. Now, grit channels, basically whatever solid particles that had escaped through the screenings will end up in those grit channels, and basically they are long, narrow grit channels. And the reason for that is so as to keep the velocity of the water quite low, so that those solid particles that were in suspension that passed through the screens are now able to settle down before the water goes to the following water treatment stage. So let's start off with the screens. Okay. As we had said, for instance, a screening is whereby we are removing solid particles through your screenings, and they're normally diagonally shaped, and basically they look like forks. So water will normally go through these forks or screenings, okay, and solid particles then will be held up under those screenings. There are different ones. There's the fixed bar screens, there's a mechanical one, there's also a hand one. Basically, in a water treatment works and in a wastewater treatment works, in my opinion, you would need both, whereby you'll have the automated one, the mechanical one, and also the manual one. The reason for that is because mechanical or automated devices normally fail, need maintenance every now and again, and also we've been facing a lot of load shedding. So in order to overcome that, you will then use the manually operated one, so that you still be able to treat your water. So that just boils down to your screenings. At times you'd also get two screenings, okay, the first one, the second one. What would then be the difference? The difference would be the openings in between these bar screens, okay. And for instance, on the first one, since we're having, if you're going to be having two, on the first one it will have bigger openings, maybe about 10 millimeter in openings. Then the second one would vary between 1.6 to 3 millimeters perhaps. The reason for that is so as to hold back screenings, solid particles that are much bigger on the first one, and then the smaller ones pass through the first one, going into the second one, which has much smaller openings, and then they'll be able to be held back so as to not to go to the following stage. So that just covers the screenings, and then we'll quickly then look at our pre-chlorination after this. Lastly, before we forget, when it comes to screenings basically after we've collected those screenings, they need to be disposed. Okay, there are various ways of disposing them. Firstly, we can either bury them. Secondly, we can burn them. And then lastly, we can basically use a macerating machine. It's like a shredder. You cut them up in pieces and also end up just burying them at the end of the day. So that's how you basically dispose your screenings after you've collected them from this process. So guys, now we'll be looking at pre-chlorination, whereby we're adding a bit of chlorine in order to control the algae. So in order basically to be able to do that, we need to know the flow of the water. And normally each and every chemical that comes from the manufacturer, you will be given a certain dosage that you need to use in order for it to work at its best, basically. Okay, so let's first start off on how to get a flow rate. Okay, so let us say we are given our water flows through a conduit. Our conduit is perhaps 160 millimeter in diameter. So let's say that's our conduit. It's got an inside diameter of 160 millimeter. And basically we need to get the area of that. So we say our area is equal to pi diameter squared over 4. And that's pi multiplied by the diameter. You just need to convert from 160 millimeter to meters, so that will come to 0.16. You just basically divide that by 1,000. So we square that up and we divide that by 4, and we take our calculator, punch that in, let's see, and then check how much we actually get. Pi multiplied by 0.16 squared divided by 4, and it comes out to 0.02 meter squared. Okay, so that is our area in a nutshell. So we'll then take that area and it will help us in getting our flow rate. But before we get to that stage, so we said we have our area as 0.02 meters squared, and we also need a velocity again. So let us say the velocity is given already as, let's have a ridiculous number like 40 perhaps. We have 40 meters per second. Okay, that's the speed at which the water is going at. Okay, so we need both of those, and there's a common formula that we can use, basically, that goes like flow rate, which is represented by Q, equals to area multiplied by our velocity. So we've got our area as 0.02 multiplied by our velocity of 40, and that comes out to 0.02 multiplied by 40. That comes out to 0.8 meter cubed per second. Okay, so we'll just try and convert the time per time unit perhaps to minute, and it will help us further when we are calculating the amount of chemical that we actually need. So basically when you have seconds, it becomes a bit more clumsy. So we said, for instance, we've got 0.8 meter cubes per second as our flow rate. So that's our flow rate as 0.8 meter cubed per second. Okay, so we'll just convert this to minute perhaps. So this is what I just normally do. I find it a bit more easier. I just say that's per 1 second, and then in order to convert seconds to minutes, you'll then divide by 60. So let's just punch that in and see what we get. So that's 0.8 divided by 1 divided by 60, and it comes to 48 meter cubes per minute. Okay, so basically that is our flow rate, 48 meter cubes per minute. We'll just keep that in mind. We'll just jot it down. Let's say that's our flow rate as, what did I get now? 48. So it's 48 meter cubed per second. Okay, and then now we need to go to our formula for basically calculating the amount of chemical that we need. Okay, as we said before, there's a certain dosage that we normally get from the manufacturer, saying that their product basically will work best when it's used in such a way, in such a dosage. Okay, so let's say, for instance, for chlorine, let's give it let's say it's 30 perhaps. Okay, let's say it's 30 milligrams per liter. Okay, that's how it normally come about. So in order to make it compatible with the flow rate that we get, in order to calculate the chemical needed, we need to convert this. Okay, firstly, as I said earlier on, I find it more easier just to put like this. This is 30 milligram per liter. Okay, so we want to convert this to grams. We'll just divide that by 1,000, and we want to convert liters to meter cube. Then we'll also divide this by 1,000, so those thousands cancel out, and basically we end up having a dosage. Let's say dosage for D will end up having 30 grams per meter cubed. Okay, so that's our dosage. We now have our dosage, also have our flow rate. Okay, so just rub that off, and now we'll calculate the amount of chemical needed in order basically for chlorine to work at its best, so that you can control the amount of algae and basically try to disinfect the water at an earlier stage, as much as it will also be disinfected right at the end. So basically, let's say we'll have the chemical that we want equal to the dosage multiplied by our flow rate. Okay, so we said the dosage, we calculated it to 30 grams per meter cubed, and our flow rate on the other hand came out to 48 meter cubed per minute. Okay, so basically if you're looking at it, the meter cubes will cancel out, and let's just calculate how much we have over there. So that's 30 multiplied by 48, that comes out to 1,440 grams per minute. Okay, so basically the device that you'll be using in order to feed this chemical into the water, okay, you need to set it to that. Okay, for every minute you need to be basically feeding 1,440 grams of chlorine into your flow, basically into water, in order for the chlorine to work at its best. So now lastly, under our preliminary treatment, we have pre-sedimentation, okay, whereby I said it happens under your grit channels. So what really happens under a grit channel, basically the solid particles that pass through our sedimentation goes into our pre-sedimentation, that pass through the screens go through our pre-sedimentation. So what really happens under the pre-sedimentation is those solid particles can be a sand, gravel, debris, all of those fine, smaller solid particles then get a chance by having a slower velocity, and that chance is basically they are able to settle downwards, and they need to settle and be removed from the system for the following reasons. Look, if you have solid particles in your system and you also have pumps in your system in order basically to pump the water from one stage to another, those pumps might get damaged from those solid particles, because remember, pumps are moving mechanical devices, so you need to have less solid particles that won't interrupt your pumping. And also another reason why we need to remove these solid particles, remember, we'll also be pumping this water through pipes. Okay, so the more of these solid particles that you get in pipes, it's going to be a challenge, because they'll end up clogging. They're going to settle in your conduits pipes, and they'll build up to such a stage that they end up clogging the pipes, and you get a lot of bursts happening how the water treatment works. Okay? So basically that covers that for our preliminary treatment in terms of all three: your screenings, your pre-chlorination, and also lastly your pre-sedimentation. Our next step is coagulation. So let's say that's our second step. So basically what happens under coagulation is that water moves from our preliminary stage into our coagulation, and during that move basically we'll then dose some coagulation aid. Okay, as we had stated previously, it might have a negative charge and the water might have positive charge, and basically they'll be mixed together at very high velocities. It can be mixed with a propeller. It can be mixed basically as the water is going from one stage to another. It will be dosed during that stage. So, and the reason for that is so that that chemical that is used, it can be spread out evenly. Okay, speaking of the chemical that will be used, there are various chemicals that can be used. There's ferric chloride, there's aluminum sulfate, there's lime, there's polyelectrolytes. There are a vast number of chemicals that can be used as coagulant aids, or also known as flocculants. And basically the reason that there are so many of them is because all of them have got the advantages and disadvantages. And for instance, let's take lime will increase your pH level, and so basically you'll alternatively look for another one. Look at the advantages of polyelectrolyte pads or aluminum sulfates. And basically it also boils down to the type of water that you have, and then that will guide you in which chemical that you will use. Basically that will be based in terms of the characteristics of the water versus what the coagulant aid will basically do. So speaking of that, coagulation, it will be at high speeds in order again for the chemical to be spread out evenly in all of the water, and then that will then be followed by flocculation. And basically now under flocculation, the high speeds that we got under coagulation, it will now be slowed down. Okay, the reason for that is so as to, for those suspended flocks, basically we'll now call them flocks. Basically there were suspended solids under our coagulation, but because of the chemical that was added, now those suspended solids are able to come together, they clump together, and that's possible under flocculation because now the velocity is very slow in terms of rotation, and those chemicals, since those are suspended solids, since we had used the coagulant aid, they're able to attract each other, they're able to clump up together. Okay, by so doing, the density of them changes. As we had said on the previous session, our density has got a unit of kilograms per meter cube, basically. So if kilograms changes, that's our mass. Okay, by mass changing, it becomes heavier. Then when it becomes heavier than the water, what will happen? It will sink down. Okay, but when that stage now comes by, we will then be talking about our sedimentation. So we said we'll then have our sedimentation. So those flocks that basically clumped up together under flocculation, now we're at another stage of sedimentation. Basically now we are trying to separate the solid particles and the liquid. Okay, so those flocks are much heavier, as we'll have, let's say we'll have our Datman sedimentation tank over there, and we'll have our solid particles. Okay, our flock, and that flock basically will settle downwards because now it's becoming heavier. It has changed shape, it has changed mass, basically it has changed density. So it will come down at the bottom of the tank, of your sedimentation tank, and by so doing, that will then be called our sludge. And basically after some time, hopefully most of the solid particles that were out there of that flock was able to settle downwards to form the sludge, and then the water will then go to the following stage. So when looking at, for instance, your sedimentation, there are different sedimentation tanks that are used. There's your hydrostatic sludge removal tank, there's a horizontal tank, there's a circular tank, there's also a Dutman sedimentation tank as well. So let us say you then be asked to basically get the volume of a, let's say, your Dutman sedimentation tank, for instance. Okay? Just like the one that we have drawn now. Let's just make it at a smaller scale. And basically you are told in one question that you have a conical part to it, and there's just a circular part to it, and you have a length, a height. Okay, you are told that the height of the conical or a cone part of the tank, let's say perhaps it's 5 meters, and then the height of the circular part of the tank is perhaps 4 meters. Okay, and then you'll also be given the diameter of the tank. Let's say the diameter of the tank is about 7 meters perhaps. Okay? So the formula that will normally be used would just be, I like to do it in this way. I just find it a bit easier, whereby I differentiate the two. I'll have volume 1 and volume 2. Okay, so I'll just have my volume. I'll just have my volume and say that's my total volume equals to volume 1 plus volume number 2. Okay, and I'll just do it like this. It's a common formula that's used. Basically we have our circular cylindrical part, which is the volume 1. So we're also given our diameter, so that is easy. It's just pi d squared over 4 multiplied by our height in such an instance. So that represents our volume number 1. And then we'll go to volume number 2, which is the conical part of it. Still the same. It will be pi d squared over 4 multiplied by height over 3. Okay, so that's the only difference. I just like doing that way. Some other people just prefer having the height then multiplying by 1 over 3. Okay, either way it's still the same, but I just find it easier for me to just say the height over 3. Okay, and then we'll have our pi multiply our diameter is 7 meters, 11 squared over 4 multiplied by our height for the conical part of it is, for the cylindrical part is 4 meters. So we'll just close that off under volume 1, and then volume number 2, say it's pi. The diameter is still the same, because remember that just comes down like that. So our diameter is still 7 squared over 4 multiplied our height is 5 meters over 3. Okay? So that's our second volume. So let's just quickly punch those in. Let's look at the first one. It's pi multiplied by 7 squared over 4, and then we multiply all of that by 4, close our bracket, and it comes to 153.938. I just like rounding up to the third decimal. And then the second volume, So let's just quickly store that. Our second volume would then be pi times 7 squared over 4. Multiply all of that by 5 over 3. And that comes out to 64.141. So the total now comes to 153.938 plus 64.141, and our total is 218.079 meter cube. Okay, so basically that's how you calculate your volume for a Dartmouth sedimentation tank, whereby you've got a conical part and also just a normal cylindrical circular part of the tank. So the next step after getting the volume of our tank, our sedimentation tank, okay, we said it's 218.079 meter cubed, okay, so that's our volume. The next thing the next calculation we need to do would be our retention time. So basically our retention time is how long it takes for the water to fill up the tank, okay. So we need to get that time and basically see how long it will basically take, okay. So the retention time, I just normally use this in order to get it, and that's our time over there. So it will be time equals to the volume over our flow rate, okay. So the flow rate, let us say perhaps it's maybe 5. Let's say we are given a flow rate of 5 meter cubed per second, okay. So we'll have our flow rate as 218.079 divided by 5, so that's meter cubed, per second. So that comes out to, let's quickly calculate it, it's 218.079 divided by 5, and that comes out to 43.616 seconds, okay. You can always convert that to minutes, hours, days, it does not matter really, but basically that's how long it will take to fill up that tank with that volume using that flow rate. Our next calculation now is calculating the upward flow velocity. So basically this velocity is just when you're having our tank like that, okay, water is flowing in, and we just need to know how basically the velocity it will take for water to rise up, hence the word upward flow velocity, okay. So let's just put that off. So we said we would have our so that will be our upward flow velocity equals to let's say our flow, our flow, it was in now. Our flow is, we need to convert it to meter cubes per hour, okay, and the one that we previously calculated was in meter cubes per second, divided then by our area, the area of the tank, and the area is in meter squared, okay. So we have that formula that represents our upward flow velocity, and as I had said, with our flow, our Q, we were given as, in fact we assumed 5 meter cube per second. So let's say that's our Q, that's 5 meter cubed per second. Now we need to convert it to hours. So just say that divided by 60, divided by 60. And let's grab our calculator and see what we get. So it's 5 divided, then it's 1 divided by 60 to convert to minute. And then we divide it again by 60 to convert it to hours. So it comes out to 18,000 hours. Okay, meter cubed per hour, sorry. That comes out to 18,000 meter cubed per hour. So that's our flow rate. And then we'll just take that flow rate. So we said it's 18,000. We'll just quickly store it. And we also have our area, which we had calculated earlier on, just that we rubbed it off. We said we are using our diameter, our diameter of our tank. We said it's 7 meters. Okay, so we just have to calculate our area, because earlier on we just calculated the whole volume of the tank. Now we need to calculate the area of the tank, and basically that is pi d squared over 4, pi multiplied by 7 meters divided by 4, which comes to pi multiplied by 7 squared divided by 4 comes to 38.485. We'll then store that again. Okay, so we go B, 38, there, 1,000. Now we have both our flow rate in meter cubes per hour, and we also have our area in meters squared. So we'll say Q equals to 18,000 meter cubes per hour divided by our, so we've got our 18,000 meter cubes per hour, basically, which is our flow, and we'll divide that then by our area, which is 38.45. Let me just recheck. There's 38.485. Okay, and then we'll just say 18,000 divided by 38.485, and the unit for this is meter squared because it is our area. So it's 18.3 divided by 38.485, and our answer comes out to 467.715 meter per hour. But other books basically just leave it as meter cubed per meter squared per hour. Either way, they're the same, because those cancel out, then you end up with meters per hour. And in any case, velocities, that's what you normally get. But with upward velocity, they just love leaving it as it is. So basically, that is our upward velocity. That's how it's calculated. That's the formula for it as well. So our following stage process is stabilization / also known as softening. Basically, after the chemicals that we had added on our previous stages under our coagulation, flocculation, those chemicals that we had used, for instance, lime, would tend to raise the pH of the water. Basically, it will be unbalanced of some sort. It will be more acidic in a way. So by coming to the stage, what we'll then do is pump in carbon dioxide. Carbon dioxide then will tend to try and neutralize our pH level, because as we had said before, our pH ranges from 0 to 14, and when it's neutral it should be around 7. Basically anywhere between 5.5 to 8.5. So but at neutral it's normally at 7. And thereafter, uh, the stage that will follow our stabilization and softening will be filtration. So we get various filtration beds, if I can put it like that. There's slow sand filter, there's rapid sand filter, there's pressure sand filter. But the most common one for normal sized type of water treatment works would normally be rapid sand filter, and the reason for that is that it's got a back washing type of mechanism whereby you don't need to take off the top layer of your filtering media in order to try and unclog it after it has clogged up, because remember this is a filter. What is its main purpose? The main purpose of it is basically to filter out solid particles that weren't able to settle down under sedimentation. So basically that's one of the purposes and functions of it, and it's one of the most important stages, because if water is not filtered out properly, solids are not filtered out properly, those solids will tend to go to the disinfection, and we'll tell you more about that when we get to it. But since now we are here under filtration, let us say we have a filtration bed having dimensions, let's say that's front side of it. Okay, so let's say the length of the filter bed is about 15 meters, and the width of it is 7 meters. Okay, that's our filter bed, and basically we have our sand. Below that we have our gravel. That's where the water is going to be filtering down from. Basically there will be those tiny voids whereby the water can go through, but solid particles will be held at the top. Okay, so we'll have our flow rate, water getting in, and the water basically will try and filter through it. So what do we really want to do now? What we really want to do now is basically to get the flow at which this water is going to exit. Okay, so let's say we have that, and basically that's our area that we can calculate. Simple, it's 15 multiplied by 7, that comes to 15 multiplied by 7 comes to 105 meters squared. Then our next step basically is to also get, in most cases we normally be given the, they say it's the flow rate, but really it's more like the velocity, but nonetheless you need to get the flow at which the water is penetrating or filtering through. Okay, so let's say it's filtering at a rate of 3 meters per hour. So for every hour, 3 meters of that water is going to filter through. Okay, so now we need to get the flow rate at which this water has filtered through. Okay, so basically we would say flow rate is Q in a way equals to our area multiplied by that velocity slash flow rate in a way. So we'll just say A multiplied by flow, just put like that. Okay, so our flow rate is 105, our area, sorry, is 105 meters squared multiplied by our flow rate, which is already given as 3 meters per hour. Okay, so that comes to 105 multiplied by 315 meter cubed per hour. So that's the flow rate at which this water is able to penetrate through these voids of sands and gravel and so forth. So basically that sums up our filtration. And before summing it up, in fact, we had earlier on we had mentioned that we have these various or different types of filtering beds. All of them have got the advantages and disadvantages, and this one basically is most commonly used because of its advantages. And basically when it clogs up it becomes easier. It's not really like this. It would normally have valves, I think, coming out over there, basically to come out in reverse and pump up whatever has filtered through over here, and then the water will go out in reverse over there. So yeah, in a nutshell, that is our filtration. So when it comes to water treatment stages, basically this is our final stage, which is disinfection. Okay, it's whereby, as you can hear from, you're disinfecting, basically trying to kill off any bacteria that's left in the water. And basically, if you recall from the previous stage that we had spoken about, which is filtration, we had said that you should try by all means to get rid of solid particles. The reason for this is that when now the water is in this state, which is disinfection, and it still has solid particles and bacteria, basically that bacteria that's there won't be able to be killed by the disinfectant that we'd be using. In most cases we'll be using chlorine, but there are others that you can also use. But this chlorine won't be effective because the bacteria will hide inside those solid particles. So hence it's so important to go through all these previous stages that we've gone through already. And another thing, chlorine is normally supplied in two types of containers. You've got your 68 kilogram one and your 1 ton, which manufacturers normally supply water treatment plants with. So that's how they normally operate with those. And with chlorine, as it's working, meaning that as it's killing off, destroying off, or disinfecting the water, it's basically being used up. Okay, hence it's also important to also look at chlorine residual. How do we look at chlorine residual? There are two tests that are normally done. For instance, there's the DPD test and the orthotodylene test, which are very accurate, that you can use basically to look at how much chlorine is still left. Do you still have any chlorine left when the water gets to you at home, for instance? Because normally what would happen is that the water treatment works would be so far from your household in such a case that by the time the water gets to your household, there's no more chlorine. Basically, that's also very, how can I put it? There's a solution to it. And the solution to it would be basically to find a middle point or a command reservoir that would be nearer to the residential area that normally doesn't have enough chlorine inside that water. So what would the municipality do? They would just normally put in more chlorine inside those storages, those reservoirs, so that you still have enough when the water gets to your households. So basically that sums it up when it comes to water treatment stages and some of the calculations that are involved with it. So please do not forget to like the video and also subscribe, so that the next time I post these videos, you can be able to get access to them and they'll just show up on your YouTube. And lastly, I'll also try by all means to upload each and every week some of these videos, so that we can basically keep up to date, as well as with you guys. You can be able to access all of this information in case you need to use it every now and again. Thanks a lot for watching the video.